Welcome. In this video, we will focus on truncation errors and true errors. And by the end of this video, you will be able to identify a truncation error and its meaning. And you will be able to calculate true errors and true relative errors. So what are truncation errors? Well, truncation errors stem from the fact that computers basically can only do addition and by extension multiplication. Now, subtraction and division can be expressed as addition multiplication as well. So let's just say for general purposes that a computer can only do addition, multiplication, subtraction, and division. But how would a computer evaluate, for example, the sign of a number or the e to the power x, where x is some number? How would a computer do that? Well, we would need to express these functions by the basic functions, the basic operators, plus, minus, times, and divided by. So we have to express sine or e or any other complex function that we want to evaluate as a combination of basic operations. How do we do that? Well, that's where Taylor series come into play. So here's a quick recap on Taylor series for a function f of x that we will expand around a point x naught. If we want to calculate the function value at some arbitrary x, knowing only the function value and its derivatives at a different point x naught, we can calculate f of x by f evaluated at our point x naught plus the distance x minus x naught times the first derivative of f evaluated at x naught plus 1 over 2 times x minus x naught squared times the second derivative of f evaluated at our point x naught plus 1 over 3 factorial times x minus x naught cubed times the third derivative of f evaluated at x naught, and so on and so on. There are infinitely many terms. And if we come to the nth term in this series, then we have 1 over n factorial times x minus x naught times x minus x naught to the power n times the nth derivative of f evaluated at x naught. But there are infinitely many terms to make this an equality. Okay, so let's do just an example for this. Let's say we want to calculate the sine of x, and we're going to use x naught equal to 0 to expand the function, the sine function, around this point. So let's write the Taylor series. So we have f of x is equal to f of x naught. F of x is the sine of x, and x naught is 0. So we have the sine of x is expanded as the sine of x naught, the sine of 0, plus x minus 0, so x minus 0 times the first derivative of the sine is the cosine. So times the cosine evaluated at x naught, so times the cosine of 0. Plus, next term, 1 over 2 factorial times x minus 0 squared, that's just x squared, times the second derivative of the sine, which is negative sine evaluated at 0, so times minus sine of 0. Plus the next term, plus 1 over 3 factorial times x minus 0 x cubed times the third derivative, and the third derivative of the sine is negative cosine evaluated at 0, plus and so on. So there's infinitely many terms. The next one would be 1 over 4 factorial x to the power 4 times the fourth derivative, which is again is the sine of 0. And then we come to the fifth term and so on, right? The fifth derivative is the cosine evaluated at 0 and so on. So there's infinitely many terms. Now we know from trigonometry that the sine of 0 is 0, so that term drops out. We know that the cosine of 0 is 1, so we just have x times 1, so just x for this term. Then we have, again, the sine of 0, that's 0, so this term drops out. And then we have plus 1 over 3 factorial, so that's 1 over 6 times, there's the cosine of 0, which is 1, and the minus sign, so we have minus x cubed divided by 3 factorial. The next term contains a sine of 0, which is 0, so that term drops out. And then we have again the cosine of 0, which is 1. So plus 1 over 5 factorial times x to the power 5. And now there's infinitely many terms, right? So let me give you the next several terms here. We have then minus x to the power 7 divided by 7 factorial, plus x to the power 9 divided by 9 factorial, minus x to the power 11 divided by 11 factorial, and so on, infinitely many terms. Okay, so let's do an example, and let's evaluate the sign of pi over 6. Right? In this formula, x would be in radians, so pi over 6 here in this example. So let's just plug in x is equal to pi over 6. So the sign would be pi over 6 minus 1 over 3 factorial pi over 6 cube plus 1 over 5 factorial pi over 6 to the power 5 and minus 1 over 7 factorial pi over 6 to the power 7, and then on to the next term plus 1 over 9 factorial pi over 6 to the power 9 minus, well, you see the drill, 1 over 11 factorial pi over 6 to the power 11. Now the important thing is that we have now expressed the sign of x, where x is just pi over 6, some number, as just a combination of basic operations, right? Plus, minus, times, divided by, even though sine is a quite complex trigonometric function. So these are only basic operations, but we need infinitely many of them, right? Infinitely many terms. None of the higher derivatives are actually zero that we could just disregard. There are infinitely many terms for us to be exact with this formula. But we can't do infinitely many terms, right, if we want to calculate and do something. So we have to truncate this series. And that truncation introduces a truncation error. And the error that we make when we stop summing up additional terms is just equal to the sum of the terms that I'm cutting away, right? So if I go all the way to through the first t terms, then my error will be the sum of the t plus 1 term all the way to the infinite term. So the sum from t plus 1 to infinity of 1 over n factorial x minus x naught to the power n times the nth derivative evaluated at x naught. So let's do a simple example, and I'm just going to use MATLAB to find the actual numerical values. If we were to keep only the first term, right, and we truncate from the second term on that we have in this series. So our x would be pi over 6. The error would be the sine of x minus x, and x is pi over 6, right? That's our expansion just using one term. Our truncation error would be negative 0.0235, and so on. You see the number here. So truncating numbers or truncating series will introduce a truncation error. Okay, so now for built-in functions in MATLAB and other computer programs, like the sine, the cosine, the exponential, enough Taylor series terms will be used such that the truncation error is comparable to the round-off error. Remember, we only have a finite number of digits available to store our numbers, so it doesn't really make sense to use more terms in our Taylor series if we cannot store that result. Okay. In general, though, the truncation error depends on the specifics of our numerical algorithm. The example that I've shown here was using the Taylor series as in a numerical algorithm, but throughout the semester we will see other numerical algorithms that will be truncated and have associated truncation errors. Now, I would like to point out that, of course, when we do these calculations, each one of these operations, these calculations, they do have round-off errors as well, right? The round-off errors are always there on top of the truncation errors. Now, in general, if we have quite complex, complicated numerical methods, it is generally the case that the truncation errors are much larger than round-off errors. That is not the case for these built-in functions like the sine and the cosine, but for most of the numerical methods that we will cover in this class, the truncation error will be larger than the round-off error. Okay, so we talked a lot about errors, so let's just, for once and all, define what we mean by errors or true errors or total errors. So the definition of the true error is the true solution minus the numerical solution. And that error, right, if the numerical solution is the result of some complicated computations that have truncations in them, then that error consists of both truncation error and round-off error. Now we can then also define the true relative error, which is basically just the true error divided by the true solution, or the true solution minus the numerical solution divided by the true solution. Now these two definitions here, the true error and the true relative error, are pretty straightforward. They only have one major problem, right? And you probably can spot the problem. We need to know the true solution. And I said at the beginning of this class that the point of numerical methods is to solve problems where we will not know a true solution. And in order, though, to calculate the true error or the true relative error, we would need to know the true solution. So therefore, these definitions of a true error or a true relative error, they're typically only useful if we want to test our numerical methods. For applications without true solutions, we will need additional measures that quantify the quality of our solution. And we will introduce those throughout the class in this semester. Thank you for watching.